believe that we know how do radio pulsars lose their rotational energy, we can estimate their magnetic fields in standard way, just extracting them from the spin-down law. To calculate B in such a way, we need to know pulsar period derivative, which are easily to be determined. But also we need to know pulsar magnetic obliquity, the maximum magnetic angle, the angle between the spin axis and the magnetic axis, pulsar radius and moment of inertia, or pulsar mass and the equation of state. And this information is quite hard to be extracted from the observations. But it seems there are some tricks that can help us to solve this problem. First of all, it is convenient to deal with the logarithm of the magnetic field. In that case, this formula can be rewritten as a sum of two terms. First of them is the classical, standard, well-known and widely used magnetic dipole estimator of pulsar magnetic fields. And second one is the additional correction term, which absorbs the information about the real pulsar radius, moment of inertia, and magnetic angle. More precisely, it absorbs the information about how the pulsar radius, moment of inertia, and magnetic angle deviates from the classical values assumed in this formula. Of course, we are unable to calculate this correction term for an individual pulsar. But what we're able to do, we can constrain the distributions of the magnetic angles, masses of radio pulsars over all pulsar population. We can impose some reasonable constraints to the equation of state of radio pulsars. And finally, we can calculate the distribution of this correction adopting some equation of state, and hence can calculate the distribution of the magnetic fields for an individual pulsar, just assuming that the distribution of this delta B is universal and is the same for every pulsar. So this is the idea, to use this correction not in a deterministic way, but in a statistical one. To calculate this distribution, we need a couple of initial distributions. First of all, it's the distribution for the magnetic angles. There are many methods to reconstruct the distribution. We have adopted the data derived by Rankin and parameterization by Zhang. But also we have checked out the more conservative assumption about isotropic inclination angle, isotropic obliquities for radio pulsars, and as you will see a few minutes later, the particular choice of the distribution of magnetic angles affects weakly to the final result, to the final distribution of delta B. And this is what we actually expect to see, because pulsar spin-down luminosity, as we think, depends weakly on the magnetic obliquity. Masses of the isolated pulsars are unknown at all from the observation. But there are a number of binary systems with neutron stars, which, as we believe, suffered quite short or weak accretion episode. So neutron stars in these systems, as we see, has masses that are close to the their birth values. And this distribution probably can be used for constraining the masses of the isolated pulsars. We have used the distributions obtained in this work by Ozil and Freire. This distribution is from the Bayesian analysis of, I think, 80 or 20 binary systems. And finally, the equation of state. There are many propositions, reasonable propositions about the equation of state of isolated neutron stars, and we have compiled a list of 22 of them, which we consider the list. We consider to be more or less representative one, because we have included to this list the equation of state that were constructed by means all basic theoretical approaches, which theorists use to constrain the equation of state. So here the radius to mass relationship, moments of inertia of neutron stars are simply proportional to the mass, and these curves are the delta B, it's a correction, logarithmic correction to the magnetic field, calculated for an aligned rotator. It means for the magnetic inclination equal to 90 degrees. And you see that within the most probable interval of masses of radio pulsars, this correction is equal to minus 0.5 dex. It means that classical magnetic dipole estimator systematically underestimate magnetic fields up to half orders of magnitude. So we have calculated distribution of delta B correction, the additional correction, for all these equations of state. Here they are. These distributions are close to, every of these distributions is close to Gaussian one, with the averages spans from minus 0.55 to minus 0.25 dex. And every of these distribution has quite small width, less than 0.1 dex. It's very important. And in general, if you don't want to deal with the choice of your favorite equation of state, you're able to average all this distribution to make a mixture probability density function, simply assuming that all equation of state you have in the list has the same chances to be realized in nature. And then you can get the generalized distribution. It's for anisotropic obliquities and for isotropic obliquities. For anisotropic obliquities, it's here. It's average value of the correction and its width of this distribution, or in a linear form. If you want to get unbiased value of the magnetic field, you have to multiply classical magnetic dipole estimator to the factor approximately equal to 3/7. What is important that this correction is appeared to be statistically independent on the magnetic dipole estimator. I will not tell you about the details, how you can explain it. Please see our paper. But it can be shown also with some simple simulation of pulsar's evolution, pulsar's magnetic angle evolutions, and indeed we see that there are not any correlations, even if we assume an exact correlation between initial magnetic angles and initial periods of radio pulsars. And if so, then we can assume that we can consider the width of the delta B distribution as the formal uncertainty of our estimation of magnetic field. So this is what we want to make a statistical analysis. Another component of the statistical analysis is the pulsar ages. We have compiled a list of 76 pulsars with independently known ages. For the youngest of them, we have adopted ages of the supernovae and not associated to these pulsars. This is the list was taken mostly from these two papers. And another 54 pulsars has the estimations of so-called kinematic ages. The kinematic age is the time which pulsar needed to achieve its current galactic position when it's traveling from the galactic disk. You know, pulsars are believed to be born within the galactic disk. They obtain a huge kick and then escape away from the galactic disk. And there are, in some sense, two types of kinematic ages. The well-constrained kinematic ages for younger pulsars, for which a pulsar distribution of the kinematic age is quite narrow and can be approximated by two-sided asymmetric Gaussian, and high-aged pulsars, for which we can say that they have intersected the galactic plane just once for their lifetime. The posterior distribution for their kinematic ages are very wide, has a multi-peaks, very complex. We simply approximate them, assume for them a uniform distribution, very wide uniform distribution of their real ages. This is our pulsar subset, 76 pulsars overplotted on the classical PP dot diagram. Small dots are the normal rotation-powered pulsars. You see that our subset represents this diagram, I think, quite good, except the most aged pulsars and pulsars with high magnetic fields. And this is our main numerical result. This is the plot, the correlation between the magnetic fields over ages of our 76 pulsars. The error bars along the B-axis are defined by the distribution of delta B correction, and error bars along the T-axis are defined by the distribution of the kinematic edges and edges of the supernova remnants we got in our analysis. To check the significance of this slope, can be seen by eye. To check the significance, we fit it by a simple model which has only 3 parameters: the initial magnetic field, the age of the turning point, and the main parameter we focused on is the slope, asymptotic slope of this trend. And what is important that if we assume some equation of state, the assumption about the specific equation of state cannot actually change the slope of this cloud. It can only introduce a constant shift, which is common for all pulsars along the B-axis. So to be concrete, we adopted here the equation of state BSK21, but it would be another one equation of state. This is the result of the fit, and this is the posterior distribution for the slope beta, and you see that it is far from 0 quite significantly. It equals to 0.5. It means that apparent magnetic fields decays for radio pulsars decays so as BT proportion scales as t to -1/5. It's a quite gentle decay. It's not quite very steep, but it's quite significant. What it can tell us about the intrinsic magnetic field evolution? We have undertaken the population synthesis of radio pulsars. We started from I think it's a classical work by Fashegi and Kaspi. We adopt their best model of pulsars evolution, including the death line equation, but also we made some extension to their population synthesis. We directly model the probability for the observer to observe the pulsar. We model the magnetic field evolution, and we include the magnetic field decay to the spin-down law. And also we have probed the death line, which is dependent on the magnetic inclination angle. I think Vasily Semyonich can explain you better than me why this is better than this model. I will skip some details of the simulation, but what I want to highlight is that the two basic contribution in the selection effects, as we found it, are the death line. This is the simulated pulsars for 0 beta for no magnetic field decay. It's density counterplots for the pulsars which pass the observational selection, instrumental selection. So the two basic contributions to the effects of observational selections are the death line, which naturally cuts the cloud of pulsars from the top, and the dependence of the pulsar radioluminosity from the period and period derivative. I can explain it later probably. And this, yeah. And this is another numerical result. We made population synthesis assuming various values, a set of values of intrinsic slope beta 0, and calculated the simulated slope, which we try to explain from our observations. So this is the observed slope, the observed posterior distribution, and this is the reconstructed intrinsic slope, the posterior distribution for the intrinsic slope for alpha independent death line and alpha dependent death line. So what we have here is that these distributions are quite wide and mostly shifted to the negative side. The negative values of beta means that the magnetic fields are growth, not decay, but growth. This result looks somewhat confusing, actually, but it can be understood since the width of this distribution is likely to be the statistical result from the high uncertainties in now estimations of pulsar ages and some uncertainties in the population synthesis technique. But in general, we understand that observational selection is likely to can make the magnetic field evolution, apparent magnetic field evolution, steeper than the intrinsic one. And hence, within our models, we can say that our observed slope 1/5 minus 1/5 rejects the theory models of magnetic field evolution, which are very steep at the end of pulsar life. Here we overplot the magnetic field evolution, which is barely admissible by our results, on the theoretical curves, which were kindly provided by their authors. We are very grateful to them. And you see that the magnetic fields that decays not so rapidly, mostly because a low amount of impurities within neutron star crust fits our results much better than the curves that assume a higher amount of impurities within neutron star crust. And finally, as I already said, the growth of the magnetic field seems quite confusing, and my personal view is that it is unlikely to be the case, but if one thinks that it could be real, then I would like to know that growth of the magnetic field is not an exotic process, actually. We know at least one process in central compact objects where the magnetic field being buried under the fallback material from the supernova explosion is really growing, it's emerging from the very low values to the initial one. Can the probable growth of magnetic field we found in our analysis be the result, be the tail? Can we find the tail, see the tail of this process is completely unclear. And this is my conclusion. It seems that timing-based magnetic fields, the magnetic fields of radio pulsars can be constrained from their timing with their uncertainty, which is less than 15 or 30%. The magnetic field estimator, magnetic dipole field estimator is well used, is quite good, but it is biased. So if you want to calculate the unbiased magnetic field, you have to think about the equation of state, you have to choose your favorite equation of state, or at least use the factor about 3/7, which I think is a good choice. The basic physical conclusion of our work is that the apparent trend, which is quite gentle, apparent trend in magnetic fields is quite gentle and allow only the field decay models that assume a low amount of impurities in the neutron star crust. And another conclusion, which is somewhat confusing, is that we cannot formally reject the moderate growth of the magnetic fields. Moderate growth, I mean, it's a 10% on the timescales of a few million years. So this is all. Thank you.
Thank you very much. Time for questions. Dick?
Yes, so interesting analysis. I have to admit I didn't fully follow what you were doing, but there's good evidence that neutron stars are born with a wide range of magnetic fields. So does your analysis take that into account in some way?
No, we think, well, no. Within this analysis, we assume that the magnetic field for neutron stars decays under the universal law independently on the initial magnetic field.
Okay.
So, if I understood correctly, you used a normal distribution for the neutron star masses.
Yeah.
But there was this paper from last year, I think from Antoniadis, that showed that the masses of the neutron stars might have a bimodal distribution with one peaked at 1.8.
Mm-hmm. Yeah.
And that is due to, they suggest that this is not due to accretion, but it's the birth rate of these neutron star masses that is peaked around 1.8. So how much would that affect the conclusions?
So if I understood correctly, those papers you mentioned, they have analyzed the different types of binary system containing neutron stars. These distributions have been constrained only after analysis of 20 binary system which contains neutron stars without accretion that will not suffer at any accretion. And the peak at 1.8 masses, as I understood, it can be from the accreted matter. It can fingers to the accretion in this system. So it's different types of binary systems. It can be used in this analysis. We need the binary systems which masses, where neutron stars has masses which are close to the initial one.
You may have said this and maybe I missed, but there is this neutron star with a breaking index that is claimed to be explained by field growth. Is that ruled out? I mean, you say you allow a moderate field growth. So that one, I forget the code of that pulsar. It's supposed to be, I mean, people make models with fallback accretion, then the field pops back out, etc. Is that allowed?
I think yes, but I'm not sure how big breaking indices can be explained by such a field growth. And in any case, there are a lot of pulsars with negative breaking indexes, which I think cannot be explained by this effect.
No more questions. Then let's thank all the speakers of this session. Is there an announcement of the local organizing committee?
Announcement from the local organizers. You probably know that there is the lunch organized for you during the meeting at the nearby canteen. And on the back side of your badge you have a map which shows you how to get to the canteen, and also the lunch is organized in 2 turns, and you may find the time of your turn to have lunch also on the back side of the badge. In the canteen, if you have any questions, you may ask me, for instance. I will be there, and for example, there is a special table for the vegetarians, and if you have trouble to find this table, please ask me. Thank you. Have a good lunch.